Afternoon, everybody. Welcome back to another CENG 15 lecture. We are up to, I think, 10 today. We are finally at 10. Mir is here with us. He's trying to decide if he wants to sit. And there he goes. He's down, so he's sitting now. So usually Mir is pretty darn quiet, so I don't think we need to worry about that at all. Hi, Mir. Hi. You want to be on camera for a minute? I don't know if my camera can actually make it. Oh no, it's plugged in. Oh no, I think we can see now. So let's move you. So there's Mir, sitting down here. Mir, you want to look up and say hi? Mir? No. He's very comfortable. He says that's where he's going to sit for now. He's just going to hang out there. So we'll leave Mir alone. But there's Mir. Let's see if I can get you guys back to roughly where you were. That looks pretty good. So we're going to continue with a couple of, how would I classify it? So it's not technically new stuff in the sense that the concepts that we're going to talk about today are new. I wouldn't say that's the case. They're different ways of doing things that we've already been able to do. And actually the majority of today is going to be just writing out some ideas because the actual code that we need to sort of implement these ideas is not difficult code. Again, let's not say it's not difficult. Things don't become easy or less difficult until you're a little bit more familiar with them. What I should say is it's not verbose code. We don't need a lot of code to do it. We only need a couple of symbols to do what we're going to do. So it's not verbose. So in that sense, we're not going to lose any time by just writing out the code instead of typing the code and doing a full example. So we're just going to do that as almost more of like a drawing stream than anything. Although when we get to the end of the lecture today, we'll have a little bit that we'll have to switch over to MATLAB for. Before we do that, just a couple of updates about the class. You probably know by now that UCSD is planning a return to in-person learning next week, so on Monday, i.e. the 31st. That is sort of at all of your instructors' discretion. You've probably gotten different heads up from different faculty saying this is what we're going to do for that class, et cetera, et cetera. For our class, I'm waiting for you to tell me what you want to do. So let's switch over. If you go to our Canvas site, right up at the top, as soon as you get there, there's a modality change survey I would like you to take for me. Remember that in most things, not just in classes, but in a much broader sense, decisions are made by the people who show up. So I think right now we've got about half of the class has taken the modality change survey. If you have an opinion on it, please take the survey. Otherwise, we'll do whatever everybody else decides to do, and you'll just sort of be along for the ride. When you take this survey, it is ungraded, so ignore the fact that every once in a while it'll say, like, you got the answer wrong. Like, I think the quote-unquote correct answer is 12 p.m. to 1 p.m., and if you select 3 to 4, it'll say you're wrong. You're not wrong. I just have to say, I have to tell Canvas to pick one of these. So tell me what lecture you're enrolled in, and then if we were to come back to in-person, how likely are you to attend? Keeping in mind the following point, which is that no matter what happens, whether we return to in-person or not, and when I say we, I just mean CENG 15, us, our class, NANO 15. No matter what happens, one of the lectures is still going to get posted on YouTube the same way that it does right now. It might not be me right here in my garage with Mir next to me, although he has now wandered off somewhere. Oh, he's standing over by the garage door. It will still get posted, so that will still happen. And at least one of the lectures will still be live streamed on Twitch. Possibly both of them will be live streamed on Twitch. And as I have said a couple of times about the class, no matter what happens, you can complete it remotely. Those statements are part of that. So with that context in mind, tell me how likely you are to attend if we actually switch to in-person. And then if there's anything else you want to tell me, I guess I asked this question with this particular class in mind, but if you have any concerns about the general return, you're welcome to put them here. I can't claim that I have too much influence over what the university does, but I can perhaps bring it up to our department And at the very least, I can try to take it into account for this class. And then last, unrelated to the return to in-person or the potential return to in-person, tell me if you want any modifications to our office hours. Office hours will probably remain on Zoom, except for if we do go back, those in-person lab hours, those would be both, right? You could either show up in person or go to Zoom, because it would just be me in the room, and I'd have my laptop with Zoom open, and also I'm physically there, so you could do either one. So it's more like, would you like any times changed? If they're working fine, just leave it blank or say, no, things are working fine. But otherwise, we'll review those, and then going forward, we'll make any changes on there. This survey is available until 5 p.m. tomorrow, and that will give me enough time to review the answers. And then when we meet back here on Friday, I'll tell you what the plan is. Actually, I'll probably send out a course-wide message. Excuse me. Course-wide message on tomorrow evening around like 5, after I've taken a look at the results on here. So you'll get both the message tomorrow evening, and then I'll review whatever the message says on Friday. Sorry, a little frog in my throat. Hang on. All right, let's see if that helps a little bit. Not really. Well, we'll just hope that that gets better as we go. There we go. It's a little bit better. So take that modality change survey. We'll get the results out tomorrow, and then we'll see what we're doing. And we'll move on from there. With that said, let's switch over to Excel, and we're just going to do some kind of conceptual learning today about different ways to do things that we've already done. So the example that I want to use for this one is a homework problem. Actually, 2 homework problems that you're currently working on. So remember that I said at the end of the stream on Monday, you've got everything that you need to do the homework. That is still true. All we're going to do in here today is look at different ways that you could do different parts of the homework. So if this particular part doesn't appeal to you, if it's not particularly intuitive, that's okay. Remember, it's not required to do any of the homework. But it may be a more convenient way to do the homework as you get introduced to it. So the example that we're going to do is that we're going to start at least with that stair-stepping problem. And we're just going to draw the first few steps. So that was our x-axis. And remember, we've got a 45-degree line on there. I'm not trying to get the scales correct on here. I'm just trying to show you, the general procedures that we had. So we had these 2 lines, a 45-degree line and an equilibrium curve that was kind of like a bowed out above the 45-degree line. So this line represents y is equal to x, and then the blue line that was up here, that was the one that was something like y is equal to like alpha x divided by all kinds of stuff underneath there. I don't remember exactly what the rest of it was, but that was that alpha line that was sitting up there. And then the task was to draw these 3 points that were on here. And then to go a little bit further, right? Your task was actually to keep going up, which I'll just put as dashed lines, but we're going to focus on these 3 because writing them all out takes a little bit. So conceptually, again, we're going to focus on drawing this red line. How do we, because we've already seen how we draw plots and how we draw straight lines and that kind of stuff. The stair-stepping can feel a little bit odd because there's not just a single formula that you need for it. This point down here, remember every point on a 2D plane is defined by an x-coordinate and a y-coordinate. And I'm just going to pick some numbers here. We'll say 0.1 and 0. And then when we come up to this point, remember a vertical line means the x is the same, but the y is different. And so we'll just pick 0.3 for that one. And then this one over here, remember when you land on a 45-degree line, when you land on y is equal to x coming horizontal, the one thing that you know right away is that the y value is the same because it's horizontal. And then since it's on y is equal to x, you know the x value has to also be the same. So this will be 0.3, 0.3. And then you continue that kind of pattern to do the rest of the stair-stepping as we go up. And we will call this one point 1, we'll call this one point 2, and we'll call this one point 3. For future reference, we need point 1, point 2, point 3. So the way that we've seen this previously, if you wanted to do a setup in the way that we have seen it, are a couple of different ways. One of those ways is to define the separate components and then build them all up into vectors. So for example, we can define point 1 as an x coordinate as 0.1. Then we can define point 1y as 0, right? That was our starting point. And then we can go up to point 2x, and we know that one had to be vertical, so it didn't move at all. And we can say that that has to be equal to point 1x, because it's the same thing. We can similarly define point 3, or sorry, not point 3, went too fast, point 2y. This is the one where we would have to use the alpha thing, right? We would have to use something like alpha times 0.2x divided by all that other junk that we had in there, which is fine. We can do stuff like that. And then we'll just briefly show 0.3x. Actually, instead of 0.3x, it might make more sense to define 0.3y first. 0.3y is equal to 0.2y, and 0.3x is equal to 0.3y. So we could define all of those. The way that we're going to do that right now is just focus on the numbers. Those are the formulas, but remember, we're just going to use numbers, and anywhere you see a number, you could replace it with a formula just as well. So all we're going to have is, for example, 0.1, 0, 0, 0.1, 0.2y is 0.3, and 0.3, and 0.3. So those are the numerical values, and that's all I'm going to carry around for a little bit, just so that we have a little bit less writing to do with something like that. Let me make sure that I'm not squishing. No, I'm okay. And then what would we do? Well, we needed to eventually plot that line, right? So we could say my x vector, we could build that up from individual values. So we could say this is 0.1x, and then 0.2x, and then 0.3x. And that would work just fine. There'd be nothing wrong with that. And similarly, we could define the y as the 3 y values. And I'm just going to put same here, assuming that you know what I mean when I say same, is you just build it up the same, and then we say plot y or xy. And if we wanted that to be a red line, we say quote red quote, or apostrophe r apostrophe. That will get us pretty much exactly what we need, right? It's a little bit verbose, but there's nothing here that we haven't done before, and all of that will work just fine to complete your homework. That's more or less the way that you would need to do the stair-stepping on your homework. But let's see a different way to do it. So conceptually, when you see the x and the y here, there is another way to think about those. The vectors x and y, we can think of them as column vectors. Right here, they're actually row vectors, the way that we've written them. But let's think about them as row vectors, where each row refers to either 0.1, 0.2, or 0.3. If that was the case, then we would have 0.1, 0.1, and 0.3 here, and we would have 0, 0.3, and 0.3 here. Right? We can think of these as separate vectors, or we can think of them as a matrix. So what we're going to look at now is how could we solve this problem if instead of thinking about these as separate points, which then get compiled into a separate vector for each one, what if we thought of them as a matrix? So we're going to think of this as, remember, we would call this 3 by 2. A 3 by 2 matrix, and we're going to call it M. You can call it anything that you want. Sometimes a good one that I've seen often is XY, just as a reminder to someone that this represents XY values. You could call it coordinates. You could call it anything that you want. It's okay. In MATLAB, all we're going to see are those numbers. MATLAB will not show us some of the things like x and y, or 0.1, 0.2, 0.3. It will have no idea that those are there. That's up to us to remember that this first column represents the x and that the second column represents the y. And that the first row is the first point and the second row is the second point, et cetera, et cetera. So that information will not be part of MATLAB. It will have no idea that that's the association that we're trying to make. How would we go about building up that matrix? It's usually a good idea to pre-allocate. So since we know that this has to be 3 by 2, which in your homework you can sort of just pencil in how many steps you have to make and count how many points there are. So the first thing that I would do is say that M is going to start off as all zeros, and we're going to say, give me 3 rows of zeros and 2 columns of zeros. And then we will draw what this looks like in green, so that you have an idea of what this is. What this means is that in MATLAB we'll have 0, 0, 0, and then another 0, 0, 0. Right? And that's what M is going to look like when we do that. We can now use indexing with our matrices to do the same sorts of updates that we were doing before, right? The same writing operations, where if I want to replace, let's say, this first value, right? I want that to be P1x. How do I replace that one? Indexing for matrices always goes by row and column, which is actually exactly what's written here. When we specified this, we said I want 3 rows and I want 2 columns. That same pattern works when you're trying to either use indexing to read from a matrix or use indexing to write into a matrix. So if I want to write something onto that top left corner, I would say something like M of row 1, column 1. And what do I want there? I want that to be 0.1, because that's where we had started as our first entry. If I wanted to then, it sort of depends on you, right? Which way does it make logical sense for you to build up your code? Personally, I would then look at the y value next. So then I would say, okay, well, the y is still row 1, but now it's in column 2. And now I have to do that calculation stuff, right? The end result is that it's going to be 0.3, but what this would really look like in your code for the homework would be alpha times x divided by all of that other junk. And what do we mean by x? Well, which x do you want? You actually want the x that's right underneath you, right? It's whatever your current value of x is. So you could also replace that with m of 1, 1. Right? You can look at the value inside the matrix. Now that it's already been set, it exists. You can look at that value right up there. Remember, code always runs from top to bottom. So initially, all the values are 0. So we kind of have to build this up starting from the first row on down. So it would actually look like code in yours, but we're just going to put the 0.3 here so that we know what this does. By the time we're done doing this, we would have replaced this with 0.1 and the next one with 0.3, and then we would still have our 2 zeros underneath here, and that's what M would look like at that point. As we keep going and keep going and keep going, we just build up more and more values inside of M. In your homework, what you're going to end up having to do, we can go on to the next one to kind of show you the pattern on here. Now I'm going to start working on row 2, because that corresponds to 0.2. So M of 2, 1, that corresponds to the x value at 0.2, which happens to be the same x value that I saw before. So I can say M of 1, 1. Right, I can always use indexing on both sides. I don't have to put extra variables in there if I don't want them. This corresponds to the x value for 0.2, right? And that happens to be equal to the x value from 0.1. That's what we're writing when we say something like that. And then similarly, M of row 2, column 2. This one, oh, actually, I think I messed up. This set actually comes down to where we are now. This is going to be annoying for you if you wrote this out, that I can do this, but I love doing this. We'll grab this. This actually needs to be here. because this was 0. I made a mistake there, right? Our first y value was 0. I got ahead of myself previously. This one, now our second y, that has to correspond to a particular calculation based on the alpha value. So this actually over here is not 0.1 and 0.3, it's a 0. Right, this one, we didn't go anywhere, right? We just defined that bottom point, and that's what these two did. These two handled the next line in our matrix. So it was 0.1 and 0.1. We went vertically, so the x stayed the same. That was our m2, 1. And then we calculated this value of 0.3, and the remaining values are still 0 because we haven't changed them yet. So sorry, I mixed that one up a little bit. And now we would continue that pattern, right? Dot, 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 all the way down to the last one, which in your homework I think you need 10 points. So you would still have a 10 and a 1, and you'd have to fill in what's ever over here, and m of 10 and 2, and fill in what's ever over here, right, to keep building up the rest of the m. In our particular case, we would stop at 3 because we don't have any more than 3, but you'll need a couple more than something like that. So for our particular example, as we keep putting those in here, let me shrink this too so that you can see a little bit more of our notes on the screen here. I know there's a little logo in the bottom left that's also there. So for our example, i.e. the one that we're working on right now, what is m going to look like? M is going to look like this. It's going to be a 0.1, a 0.1, and a 0.3, and a 0, and a 0.3, and a 0.3. And that's what your m will look like after you've done all of this code that we have up here. If you look at m, right, if you go look at m in the workspace right after you update the last value of m and go look at it in the workspace, it's just going to look like a bunch of numbers. You won't see the variables in the actual workspace. You'll only see the variables in the code, which is good. That's what we want. So remember, with something like this, now what we've got is conceptually this represents the x values, and this represents the y values, right? First column and second column. This corresponds to the first point, this corresponds to the third point, and so on and so forth. The question becomes, now that we've gathered the data like that, how do we use it? And that's sort of the first new idea that we have. I don't know if you count this kind of row column indexing as necessarily a new idea, maybe, but it's a fairly, I would say, logical extension of what we had before, right? Instead of going into an individual location inside a row or a vector column, or sorry, a row vector or a column vector, now it's a matrix and you just have to define the row and the column, right? You give it 2 coordinates instead of 1. But now we have a new idea, which is how do we sort of get those entire columns out, right? We need to now plot x versus y. So our new idea is colon indexing. That is like the first of, I think, 2 new ideas for today, is the idea of colon indexing. And the idea of colon indexing is when you've got something like a matrix, often you're interested in an entire row or an entire column of that matrix. So for example, our M matrix here, we're kind of interested in full columns and not full rows, but we could get either one. So what colon indexing does is it'll read or write, it doesn't matter which one, it'll read or write across all elements in that index. And when I say across all elements in that index, what I mean is a whole row, an entire row, or an entire column. Or potentially both. I suppose you could use a double colon to rewrite the whole thing, but we don't often do something like that. So as an example, we have that M that we want, right? To get the first column of M out, we can call that X, and we can say X is equal to M of what? What do we want here? Well, we want the entire first column of M. Remember, the indexing always goes row column. So when I want to use the colon, I want to say, well, which one do I want all of them, right? I want all of the indices for that particular dimension. That would be the first one. So if we say a colon, we say, give me all of the rows, and now I ask for, well, which column am I interested in? Probably the first, right? Because we defined these as X in the first column and Y in the second one. So this is saying the second index says go in and give me column 1, and this one, the colons here say give me all rows. So the result of this operation is to take out X, well, not take out, read out of M and define as X the vector 0.1, 0.1, and 0.3. Right, this is now what X will be. That's X. And you can probably guess what it would be for Y as well. It's essentially the same thing, except you're switching, you're changing the column number. You're leaving the colon indexing alone, though, because you still want all of the rows. So we can still say something like, give me M of all rows, because that's still what I want, right? I want every single row in there, but now I want the second column. And this is interpreted in essentially the same way, which is the colon says, give me all the rows, and the 2 says, give me column 2. And the result of this is that you will create a variable y, and it'll be a 0, a 0.3, and a 0.3. And that'll be y. Notice that this is now 3 by 1. Because you said, give me every row in M, but only one of the columns. So it gave you every row. There were 3 rows, and then it gave you just one of the columns. Beep. And now we can use these to plot things inside of MATLAB the same way that we had before, because we now have 2 vectors again. So we can plot those exactly the same as we did before. So I can come up here and I can say, now that I've got X and Y, I can say plot X, Y, and presumably make it red, right? We wanted a red line, so we would plot it. And that looks pretty much the same as it did previously. There's another way that we could do that. Remember, we don't need those individual variables. The X and the Y that we've got right here, this one and this one, it may be the case that we've only needed those in one place, right? Maybe we only need them here and here. If those are the only places that we need them, maybe we don't need to actually define those variables. So it would also be okay to write something like plot and just do the indexing inside of the plot command. So we could say, give me the first row, the first column of M, treat that as X values, and then give me the second column of M and treat those as Y values, and then make these red. So with something like this, this represents X and this represents Y. It's just we saved ourselves the trouble of creating extra variables, but maybe that's a little bit less readable to you. That could be the case. It's sort of a personal choice as to whether or not you wanted to do something like that, but it would be possible. That would be just fine to do something like that. Will I post these nodes? Yep, I'm going to post these. I mean, post them in the sense that when you go look at the YouTube video for this, there'll be a link in the comments. You can go in and download these notes that I've got here. As another example, which it's not necessary for your homework, I just want to reiterate that the colon operator can go in any of the indices. If we wanted to go in and read the first row of M as P1, right? Remember, P1 always looks like an XY pairing. How could we do something like that? Well, we could say P1 is equal to M, and now we don't want all rows, we want the first row, right? Only the first row, but we do want all of the columns, which in this case happens to be both of the columns. So we could say a double colon here, and that would extract the first row of M, and the end result would be that P1 would look something like, not something like, it would look exactly like 0.1 and 0, which is now a different shape, right? This is 1 by 2, because you went in and grabbed a row, and you said, give me all of the columns, and there were only 2 columns, so you got a 1 by 2. These points then correspond, if you needed them, for example, to be P1x and P2x. Sorry, P1x and P1y. And it's going to be the same shape, right? One of the 2 dimensions is going to be the same. In this case, we put the colon index, or the colon operator in the second index, and it said, give me all of the elements in there. So the result is going to be the same size as whatever we started with, because we took all of those elements. Hence, if we started off with 2 columns, we get 2 columns here. When the colon index is in the other, or the colon operator is in the other index, then you get the other dimension. So the output is always going to look like you've read out whatever row or column you're working with. It's never going to like suddenly flip and say like, well, I was expecting it to be this way, and for some reason it came out that way. If the shape isn't what you wanted it to be, then it's probably because it wasn't indexed correctly. It will never arbitrarily flip them around or anything like that. You can also go the other way too. So you don't have to only use this as a read operation. You can also use it as a write operation. So let's add some more space down here. You do have to be a little bit more careful with a writing operation because you really have to pay attention to the sign, or sorry, the shape. When you're reading things and creating variables, usually that won't cause a problem right away because you're just making a new variable, right? This P1 that we've got here, we're creating that variable. We can create it to be anything we want. So if we screwed up the indexing over here, we won't know it just based on P1. MATLAB will make P1 just fine. But if we're doing the opposite of writing into it, let's say we know P1 and we want to write it into M, then you've got to get the shape right or you'll get an error right away. So for example, if we wanted to write P1 into that first row of M, we could say take M in the first row and both of the columns. If we want to do that, if that's on our left-hand side, that's perfectly fine. We have to give it exactly the right shape on the other side. So this has to be a 2 by 1. I mean, the numbers might be wrong. I've screwed up numbers before. It wouldn't be the first time that I screwed up numbers. But this is saying that where I'm writing, the thing that I am writing into, is 1 row by 2 columns. Because M was a 3 by 2, and you're saying just take the first row and then look at all of the columns. So it's got to be 1 by 2. That absolutely requires that this is also 1 by 2. So it will not work if you say something like this. If you say 0.1 and then underneath it 0, this will cause an error. Right? If you tried to give, if you were to put a semicolon in here, which is the same thing, if we were to write 0.1 and then semicolon 0, this is an error. Right? That will not work because this is 2 by 1. It's 2 rows and 1 column, and you're trying to put it into a thing that's 1 row and 2 columns. So they have to be the same shape, not just the same element, but the same number of, not just the same number of elements, but actually the same shape. And so that can be a little bit of kind of an annoyance, unless you're being careful about how you're building stuff up. There's nothing wrong with doing it that way either. Like, that is going to work just fine. There's nothing wrong with doing that. You just have to be careful when you're setting it up that you get the indexing correct. And our last new idea that we're going to talk about in text, we're going to hit one more over in MATLAB in a moment here. You can index with more than one index. So indexing with multiple indices. And the advantage of this is, or can be seen on your random walk problem, which we'll get to in a moment. Another way to get this that we were doing right here, either writing or reading, you can give it single values if you want, you can give it the colon operator if you want, or you can give it a vector of indices. So for example, to do exactly what we just did up there, instead of M1 and then colon, we could have said M1 and then give it a vector of indices of 1 and 2. And that would do exactly the same thing that we did before, which is fine. You can do something like that if you want to, but the real power of that comes from when you are doing math with large sets of vectors and you're only interested in certain elements of that vector. So as an example, let's consider your random walk, because you have to do something like this in your random walk. You'll probably have an x vector and a y vector, because I asked you to set it up that way, or at least I showed you how to set it up that way previously. And I'm just going to focus on the x vector right now. It's going to look like, a 0, and then maybe a 0, and then a 1, and then a 1, and maybe a 0, right? Dot, 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 all the way out to the end of that. It might be, 78, 79, something like that, right? Remember, that is the x coordinate of our stepping. So we're either adding 1 or subtracting 1, or 0 to that coordinate, and we're going for lots and lots and lots of those. So this would be like our first step, second step, third, fourth, fifth, dot, dot, dot. And then I think I'm going to ask you to go out to like 4,999 and then 5,000 out here. And you'll have the same thing for y. And then one of the things that I ask you to do is read at the 10th value, the 20th value, the 50th value, right? And so one of the ways that you could do this, there's two different ways. Option 1 is what we've already seen. So if you want the 10th value of x, you say x of 10. 20th value is x of 20. 50th value is x of 50, etc., etc. Option 2 is to use this new idea of indexing with multiple indices. So here, instead of all three of those, I can say, give me x of, and then I give it a little vector of indices. You can say, give me the 10th, give me the 20th, and give me the 50th. They are slightly different. So this approach will yield 3 numbers. Yields 3 numbers. This approach is going to yield a vector. And specifically, it's going to be a 3 by 1 vector. Because what it's going to do is it's going to go in to your x vector, and let's say it wanted to grab this one, it wanted to grab that one, and this one. I don't have those indices right, but use your imagination that those are the correct indices. It's going to take all of those and it's going to bundle them into a resulting vector in roughly the same shape. So it would just look like 0, 0, and 78 if you gave it indices 3, 5, and 4,999. But that's just an example of what we wanted. That's why it looks like 3 by 1. You gave it 3 indices. The original vector was a column vector, so it's just going to pull out those 3 and leave them in a column vector. Even though the indices that we gave it, this is 1 by 3. So that is admittedly a little bit odd, right? It's just a difference of what am I using that vector for? In this case, that 1 by 3 vector of 10, 20, 50, it's not really a vector that's doing math, it's a vector of indices. And so therefore it's treated like indices in MATLAB. The advantage of this is that if you were to define something like IDX is equal to that list of vectors, right? Maybe you want it to be 10, 20, 50, right? Dot, 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 out to however many you want. You can do math based on that stuff very, very quickly, and for only the points that you want. So for example, you can say R, which is your displacement vector, is equal to the square root of X. Which X values? Just the ones that are at those indexing points, right? I don't want any of the other ones, and then I want to square them. And similarly, I want to add that to some Y values. Which ones? Just the ones at those indexing values. And I'm going to take those and square them, and then I'm going to take the square root of that. That is a powerful tool because now I don't have to create individual values for each one of those. What this is going to end up giving me is R is now going to be a vector. And R, for example, if we have 10, 20, 50, etc., the first element in R is going to be the square root of X of 10 squared plus Y of 10 squared. Take the square root of that. The second element is X of 20 squared plus Y of 20 squared. Take the square root of that. Third element, same idea, right? It just goes on down. But all of these are going to be calculated all at once, and they're all going to be stuffed into one vector like that, that has the same number of elements as the indexing thing that you had before. That's nice, right? That saves you a ton of time trying to calculate stuff because you can just define the vector, the indices that you want, and then do the element-wise operation. Don't forget to do element-wise operation, right? We need a dot caret here and a dot caret here. Don't worry about the square root because it will do the element-wise for you. But that is really nice because now I've got all of those R values in this column vector. It's going to be a column vector because most likely your X's are also in a column vector form. That's a really nice advantage of using more than one index. So there's just different use cases for each one. There's still no reason, if that is not something that sits comfortably with you, there is no reason that you can't do it the way that we've done it previously, right? Which are through this sort of an operation where you're, oops, I don't know what happened there. Where you go into your vector and you pull out individual components and then you assemble those into a different vector and calculate stuff that way. You can still do it that way. Don't worry that somehow we've broken that approach. But this approach that we've got down here, I would say reduces the amount of code that you have to write. It's a little bit more concise. So I'm going to switch over to MATLAB for one last thing. We're going to run, I'm going to give you a heads up here. We're going to run about 3 or 4 minutes over today. But it's important enough that I want you to see the whole thing. So I'll understand if you can't obviously stay for the last 3 or 4 minutes. But remember, it will be posted. So if you got to get to your next class, don't worry. It'll be posted right after lecture. But it is an important thing. We're going to run about 3 minutes over, something like that. So the last thing that I want to introduce you to is a way to see what MATLAB is doing. So I'm going to switch over to MATLAB. So this is one of the scripts that was posted from Lecture 9. First thing I'm going to do is save a copy of this so that I don't destroy it. Let's say Lecture 10B demo. And I don't care about the plot right now, so I'm going to clear the plot and delete the plotting stuff on here. I'm just interested in the code. I'm not interested in anything else. Something that looks funny on here when you run the script is, notice the workspace. There's nothing over in the workspace right now, and then when you go to run the thing, suddenly all these numbers pop up in the workspace, right? The whole script ran. Apparently it went through 100 different steps. Stuff happened. How do we see what actually happened in there? There is a way to do that. The way to do that is through MATLAB's Debugger. To enter the debugger is actually available right now. You don't have to do anything special in terms of installing anything. But to start the debugger, these numbers that you have over here on the side of your script, those are not passive objects. They're not there just to tell you what number a particular line of code is on, although that can be really helpful. They are also places where you can put what are called breakpoints. So if I click on a number, let's say I click on the number 2, that is called a breakpoint. So the little red box that I've got right here, this is called a breakpoint. What it does is it says run line 1 because there's no breakpoint here, but when you get to line 2 where I've set the breakpoint, stop. Don't run anything on line 2, just wait for me to do something. I'm trying to track something, so run up to that point and then stop. So if we enable that and then click run over here, that's exactly what happened, right? It ran right up to that particular breakpoint. Notice it did in fact run the first line because we do now have the number of steps is equal to 100. And a couple more things have happened. There's this green bar here that says you are currently waiting on line 2. There's also a message in the bottom corner down here that says you are paused in the debugger. And our 3 buttons up here have changed. Continue, which is the one on the left, says just keep going until you hit another breakpoint. So if we were to hit continue, it would go through the entire remaining portion of the script. The step one is the one that I'm usually using when I need the debugger, because if you use the step one, it will go one line at a time. One line at a time. And that's really nice because now you can actually see each variable get created, but more importantly, it gives you a way to get inside of these for loops and inside of these switch cases. It gives you a way to look at how that logic is executing when the computer is actually running it. Otherwise, those things tend to go by so fast that you might know there was a problem because stuff didn't work, for example, but it could be really hard to figure out exactly what that problem was. So putting breakpoints inside of for loops and inside of switch statements or eventually inside of if statements is really helpful. And that's what we're going to do in the last 5 minutes of class. The last button over here is the stop button. When the debugger is running, you have to say stop in order for it to sort of reset so that you're ready to run it again. So if you don't hit stop, it just won't run anymore the way that you think it will. So we can run step here. And we'll see we get the X because I clicked X. We're paused on line 3. If I go ahead and click that, it will continue on and pre-allocate Y. And remember, at any one of these steps, if you're not sure what just happened, you can run that step and then open the variable in the workspace, right? And you can see, sure enough, I've got a bunch of zeros here. So don't forget that you can just inspect the variable too. It exists in the workspace. The real power now is we are inside of the for loop. So if I hit continue here, it's just going to jump over the whole for loop and do it all at once. So that doesn't help us really understand what just happened. Another thing that I like to do is put a breakpoint on the first line of the for loop. That's the same as doing what we did before and then just hitting step a bunch. If you put the breakpoint here and click run, it will stop partway through the for loop. In fact, very little of the for loop has executed. I actually have a note here that says this indexing variable that we've got here, it really does exist, right? It just exists as a number. So if you say 2 to 100 here, it'll be 2, and then it'll be 3, and then it'll be 4, etc., etc. And sure enough, you can see that the index variable over here has been defined, and it is now equal to 2. And with this debugger enabled, we can now step through and watch each step of our calculation. So if I click step here, I get a random number, and we got a 4. And we can see now how the switch case handles the 4. The first thing that it's going to do is say, is this case 1? No, because it's not a 1, so it skips over that one. Is it case 2? No, skip over that one. Case 3, no. Case 4, Yes, that is a case 4, and now we can actually watch it step down into the case and see what it's doing inside of each one of those cases. That is exactly what MATLAB is doing when you run that debugger. You're just slowing it down here so that you can see it one step at a time, and this is amazingly useful for catching errors in your logic. Usually the errors that we get might be something like, oh, you have the wrong shape or the wrong size, or you're trying to access something that's not there. The way that we track down the actual source of those errors is very often with a debugger, because you can see exactly what's happening in each step, especially when we have something that's inside of a for loop or some kind of a decision structure like a switch statement here. If we wanted to continue running step, it would calculate its way through the rest of this, and then it will loop back up to the beginning of the for loop again, right? And I can step down through here. This one happened to be another 4, so it came down through here, it did all of its stuff, etc., etc. If you were to hit continue here and watch the index that's highlighted over here, it'll run through the entire loop until it hits a breakpoint, and the breakpoint is up at the top. This is why I like to put breakpoints inside of for loops, because not only can I use the step to make sure that the first few steps are going okay, but then once I'm pretty sure things are going fairly well, I can start using continue to really step through the rest of the loops, right? I'm already up to 14 iterations, and at any point during any of these, I can open up X and look at it and say, does this make sense? Does it make sense that it started off like this, and then everything beyond that is zeros? Yeah, because I pre-allocated it as a bunch of zeros, and we're only on step 14. So this is the power of the debugger, and we will probably use this a handful of times throughout the lecture when we want to illustrate the point of how a decision is being made, or what was being made in a particular process, right? Whatever the simulation happens to be. The real power of it, though, is when you've encountered a problem and you're not sure what's happening. And so when you come to office hours going forward, I might start asking you to enable the debugger on a particular line so that we can look at what's happening inside of that workspace. And that'll be even more important when we introduce the idea of functions, because it's very hard to see what's going on inside of functions without the debugger. So again, that was about 3 minutes over. I do apologize for that if you couldn't stick around for the whole thing, but it's an important topic and one that we're going to come back to. So I will wrap it up there. Please complete the survey that is on Canvas for a potential change in modality. We'll see what happens tomorrow. It's available till 5, and I'll take a look at it around that time and see what we're going to do. I will stick around over in Canvas chat if you have any questions after the lecture. But otherwise, stay safe, stay healthy out there, and I will see you either in office hours tomorrow or back here on Friday in lecture. Have a good one, everybody. We'll see you soon.